Welcome to Breadboarding. This is video 50 in the Breadboard 8088 PC series, and this is the fifth part of building a CGA video controller on breadboards. So our overall plan here, the first stage of this is really building a basic Nanocomp 8088 which had a 7-segment LED display and keypad. Then we built the basic floppy disk PC, so this was able to boot MS-DOS 330 off the floppy disk and had a monochrome display adapter video controller. This final stage of the project in trying to get this to run an early version of Microsoft Windows. We've already built out the IDE disk controller and booting MS-DOS from the hard disk, and in this series of videos we're getting the Colour Graphics adapter video controller up and running. In the previous video we managed to get the schematic and the layout, the breadboard layout. So this is where we left things. So we'd kind of laid out the breadboards. We've got 5 breadboards across the way here and an extra one down the bottom. So we've got our fast video RAM here, the cathode ray tube controller chip here. This is the ROM used for the character generator, and this is a video digital analog converter that provides the output signals for the VGA connector here. And then we've got a 25 megahertz oscillator here which provides the dot clock necessary for VGA output. And then we've got lots of PLDs, latches and other general logic that we need to support all of that. So we wired up these breadboard buddies for the power rails and these various connectors, and one of the things we need to do now is to check all of the chip labels and actually put all the chip labels on. So if we have a look at the chip labels, there is a video which I'll include in the description below and at the top of the screen, which includes a video talking about chip labels. This originated from Grant Searle's project, so this is the chip labels that Grant produced, and this has quite a few nice logic diagrams for a number of the common chips, and also has a lot of the microprocessors that Grant had used on a lot of his projects. Now when I did the breadboard PC, I started to build out a number of other ones here. So there's some of the Intel chips at the top here. We've also got the CRTC and the digital analog converter here as well. Now what I've also now done is for the CGA, I've done a separate diagram now. What I've got here really is the programmable logic devices, various things for the board here, and I've also done a number of the various latches and things and made sure that the pin numbering is 0 index. It goes from 0 to 7. Quite often the chips are normally numbered from 1 to 8, which isn't very useful when wiring up microcomputers. And some of these I've also reversed. You can see where it's got 0 indexed rev just means that rather than going from 0 to 7, it goes from 7 down to 0, so to fit the layout of the board a little better. What I've done then is printed all of those out, print them out in high quality at real size, no scaling. And then what we're going to do then is to stick all of those onto the various chips. We need to be careful to make sure the orientation of the chip in the breadboard is correct, and also that we put the chip label on the right way. So if we just lift the breadboards away, here's a schematic we were working on last time, and then we've also then printed out all the chip labels and they're just resting on here. So it just means that I've made sure they're the right orientation. And so what I'm going to do now is to go off and just stick all of those onto the various chips. Just use a glue stick, so Pritt stick in the UK. And sometimes you need to do it a couple of times. They sometimes come off, but generally they'll stick on for quite some time. So all the chip labels now on. So there was one I had the wrong way around, so it's important to check that the chips are the right orientation, that the label obviously matches the chip, otherwise you can have very difficult to track down problems a little bit later in the project. So now we've got all of these labelled. I'm going to press them all into the board in a minute, and what we're then going to do is to have a look at which bits of this we need to wire up first. So I'm not going to wire up all of the chips all at the same time, so to start with I'm only going to be doing a handful of them. So let's have a look at the block diagram and see which things we're going to be doing first. So block diagram here, what I've done is I've taken out all the bits which are not necessary. So to start with, we're going to be connecting up the cathode ray tube controller chip. So this is the Hitachi equivalent of the 6845. We're going to have the 25.175 megahertz dot clocks. That's the VGA dot clock frequency. which is then divided by 8 to produce the character clock, which is about 3.1 megahertz. We're going to need to have the IO port decoder, so this is going to give us the various IO port chip enables for the CRTC, for the digital analog converter over here. So this is our video digital analog converter. We're going to need to program that to put in the red, green, blue values for the various inputs that we're going to put into here. The clock programmable logic device we're going to need to do, this is going to do the dividing, and it's going to be producing a lot of the control signals to clock the latches and things like that to coordinate everything. And we've also got the horizontal synchronization signal, vertical synchronization signal, the display enable, and the cursor signals are also going into the various control logic here and are used to control the output of the digital analog converter. So if display enable is suppressing the output, then we just get black coming out of here, and the horizontal sync and vertical sync will need a little bit of processing and delaying to make all the signals look right. But to start with, we're going to keep things simple to start with, and what we should be able to see is an output which is very similar to what we produced in some of the earlier videos. And what we do in the initial testing is, rather than driving the inputs to the digital analog converter from the outputs of the various RAM and attributes and all that sort of stuff, all we do to start with for a test pattern is take some of the address outputs of the CRTC and feed those in as the red, green, blue and intensity attributes. And what we'll actually get, I'll show you on the next slide, is an example from some of the earlier parts of the project where we did a similar thing. And we also need to make sure we've got all these ports set up, so the IO ports, so that we can actually set up the palette registers for the digital analog converter here. So these are the first 4 here. And then the CRTC index and data registers are actually on the CRTC chip. And then at later stages, we'll be adding the control port, color port and status port a little bit later on. So this is what we'd expect to see out. So depending on which of the address lines we hook up the inputs, we get it cycling through all the 16 combinations of the colors. So that's red, green, blue, and then the intensity. So it's from black, blue, sort of various shades of grey, and then the lighter versions of the colours. So we should see something like this if everything's actually working okay. So the chips are going to need to wire up. First of all, we've got the digital analog converter, so I'll just plug that in. We've also got the clock PLD, so we're going to need to have the CGA clock PLD. This is the 25 megahertz dot clock crystal. We've got the CRTC here. This is the IO decoder over here. This is a constant current source, and this needs a few other components for it to actually send in the IRF signal here, which is then used for the digital analog converter for producing the right voltage levels to drive the VGA monitor output over here. Now, if you've seen any of my earlier videos, you know that I use this sort of solid core hookup wire, so I'm going to be using that. I've got a little jig here for making the 4-hole and 3-hole wires that we need. So a lot of these wires are needed for the tying the power pins to the 5 volts and to ground, and we need combinations of 3-hole ones for when the power rail is close to the side there, and then you need the 4-hole ones for when you've got to go over the other power rail there as well. So that's a useful little jig for making lots of those cables and making them more consistent using the wire strippers and my cutters as well. So what I'm going to do now is to start wiring this all up, check off the diagram underneath as we go along. What I'll hopefully then be able to do is to get the output of that test pattern that I showed you earlier on. So just going to make up some power jumpers. So this is to tie the bus rails to the various pins. Now, getting the 3 and 4 hole pins the right length is a bit fiddly if you don't use a jig like this. All I do is put the wire strippers to about 1/2 inch, which is 2.5 tenths of an inch, which is about the right length for the breadboards. And that just means that we can make these little wires a lot more easily than they could if you were cutting them individually. So just hooking up all of the power lines for the moment using our 4-hole and 3-hole jig. I find that this is easier than using the pre-cut packs of wires that you can sometimes buy as well. I prefer to have my own colour scheme for all my hookup wires here. So we've labelled the VGA connector with all the various rails there. So I need to hook up the components around the constant current source, and there's various resistors and things that need to go with the VGA connector. So we've got a variable resistor here which needs to be trimmed to about 15 ohms. We can vary that later to adjust the intensity of the video signal. Now we're just going to wire in the red, green and blue video lines. They need to be then tied to ground with 75 ohm resistors to make sure the impedance matches with the monitor. Then the output resistors for the horizontal sync and vertical sync. There's a tie to 5 volts there, and then a lot of ground signals here which are just tying all these ground signals together. Now we need to get the constant current source into the iRef, and then the blue, green and red video output signals. Just change the yellow one there to fit a bit better. Plug in the connector again. Then we just need to wire in the horizontal sync and vertical sync. Check all those things off there. So that's the vertical sync and the horizontal sync. Then check off the diagram. So though I tend to work off the KiCad diagram actually when I'm doing this, but it's useful to check off all the things when you've got a complicated diagram like this. Okay, so we've hooked up the output side of the CGA card now. So now what we're going to need to do is to sort out the clock. So this is the 25 megahertz crystal here. This is the clock PLD for which we're going to be feeding the 25 megahertz in, and then the dot clock output is just going to be going in up here. Now most of the signals on the clock PLD here we won't be using for the moment, and there is a reset line that we might just need to tie high for the moment. And so what we're just going to do now is to have a look at the schematic, work out what needs to be connected, and we'll get the clock working. So we have the 25 megahertz clock here, the PLD here, so we have the 25 megahertz signal goes in here. There's reset that needs to be held high for the moment. These are really the only main inputs. There's also high res, so we'll tie that to high for the moment because we want to run this in the 80 column per line mode initially. And then the dot clock comes out of there and goes into the dot clock of the digital analog converter up here. This should be relatively straightforward. When we start to connect up all the latches and other things, then we'll need to start worrying about all these other signals on here as well. So just zoom in. So you just need to wire up the clock output, 25 megahertz, then the dot clock feeding into the video DAC, and then tie those two pins to 5 volts. Okay, so now I need to program this PLD. Now this is based on the monochrome display adapter PLD, the clock. So it's based on version 3 of the MDA PLD. What it does have in addition is the high res input, and this will switch the clocks between the 80 column and 40 column modes. Now at the beginning we're only going to worry about the 80 column modes, and so you can see here the only real differences I've now called this 25 megahertz. This outputs dot clock, so a few changes here. We've also added a divide by 16 QD clock output, so this will be used in the 40 column mode, but for the moment all I've done so far is a dot clock will be 25 megahertz if high res is true, and it will be the dot clock divided by 2, which is QA, if high res is low. So we should be able to test that at some point in time. And so these rules have just had the extra QD rules added to them to do a divide by 16. All the other rules down the bottom are the same as we had for the last stage of the MDA project. So just going to compile this. So WinCPL is a fairly old utility. It's a little unreliable, but with the way how I run it here, then this should hopefully work. So that's compiled this successfully. So now we need to do is to program this. So we're going to go into XG Pro. So we've got the right chip here. It's always worthwhile reading the current chip. So I've got the PLD in there. So this is an ATF22V10C, and it has detected that okay. If you got it wrong, put it in the wrong way around, then it would tell you it couldn't read it. If you try and program the chips when they're in the wrong way around or not quite, pins not quite connected properly, you may damage the chip. So now we're going to load the file that we've just produced. You can see here CGA clock version 1 GED file. We now program this. I won't put the lock bit on there, so it just means we can read it. Okay, so that's programmed it, so we can put that into the circuit now, and hopefully the clock part of the circuit should now be okay. Just need to make sure we put this the right way around. Okay. Now we need to hook up the CGA IO decoder. So this is the thing that takes the addresses from the address bus and the IO read, IO write, and then produces all the various enable signals for the various latches and chips, so the CRTC and the video palette here. So we're just going to need to program this. We'll wire in the address lines and IO read and write when we actually put it in with the main board, so we'll leave those for the moment. But then we need to connect the write and the read signals here over to the palette, one's over here, and we may as well also do the 6845 chip select as well whilst we're at it. So you can see here, if we go to this particular chip and if we look at the various outputs, so we've got the CGA palette write and the CGA palette read, and we've also got the CGA 6845 chip select, and we also need to program this chip as well, so we may as well just program that now. So this is based on the monochrome display adapter IO controller. There's a few of the pins, things like floppy disk controller and keyboard controller, taken out of there because we needed a few of the extra lines here. You can see here we've now got CGA status port, 6845 chip select. This is the control port, the color port, the palette read, the palette write, and then these are all the inputs. So this one in particular goes low when the A19 to A12 lines are all low, so it means we don't need to decode all of those all the time. And then down here, the rules and things have been changed now to allow for the IO port range for CGA as opposed to the MDA. And we've also added in the CGA Colour as well. So we're just going to compile that and burn it. Compilation successful. We just have a look at the output file of that. It's always a good idea to check some of the documentation files that are produced, because sometimes you might see that there's a pin not being assigned properly. There's a few times I've picked up problems, even though it's compiled properly, may not have actually enabled the pin properly, so it's always worthwhile having a look at the doc file. So now I'm just going to burn this. Just put this back in the board, now it's been programmed. So just going to be hooking up the palette write and read controls and the chip enable for the CRTC. Now we also need to wire in the address lines. So if we look here, the RS register select 0 is A0, register select 1 is A1, and if we also look down on the CRTC, there is also a line there as well. So the easiest way to hook these up is that the A0 line will be connected to the main bus up here when we connect it to the main board. So that's how we'll do this. Just plugging in A0 and A1 over to the palette and A1 down to RS and check it off. So now we need to wire up the CRTC. So we're going to need to do the power. There's the clock. The read write is probably going to need to go to the IO write signal over here. There is the E clock signal that comes from the main decoder on the main board, so we are going to have to worry about wiring that in at some point in time. We've already done the chip select, and we also need the display enable needs to come out of here and go into the blank input over here. So there's a few things there. So let's look at the schematic. So if we have a look at the clock first, this goes to the character clock. Character clock pin 16 there, and that will normally be the dot clock divided by 8. Read write is going to go to the IO write, and again we could use the IO write over on the decoder over here because that's going to be coming in from the main board. The E signal is the only one we don't directly have, and in fact if we look on the main diagram here you can see that E comes off the main decoder here, and in fact there's also a change we need to make to this, that we've now got a CGA RAM address enable as well that is coming in. So there's a couple of lines coming in from that main decoder, so CGA RAM, the IO address 19 to address 12, and also the E signal. So those three things we're going to need to bring in from here, and we're also going to need to update that PLD at some point in time as well. And then the display enable output needs to go into the blank input on there as well. And reset, we can just tie that up to 5 volts for the moment until we wire in the main reset. So wiring in the IO write to read write, then this is the character clock, the blanking input to the video DAC, put in the power rails and then tie reset to 5 volts. I finished hooking that up, just going to check off things on the diagram. So we've done the clock going all the way up to character clock up there. We've done display enable going up to there. We've got IO write A0 and A1. We've got read write to IO write. Chip select. So we just need to remember about E. Just make a note of that so we don't forget it. And we've done reset, done ground. So apart from the data bus lines that we need to wire up, and everything else should be done now. Okay, so before we finish this video, just need to hook up the CPU buses. So we're going to need to connect the data bus for the video DAC here down to the CRTC. I'm going to just get a cable off the CRTC to go to the CPU bus initially. It's going to be wired up to various buffers and things a little bit later. And then we just need to also connect the address bus and the IO read, IO write over here to the CPU buses, and then that should allow us to be able to plug this into the main board and start testing it. So what I use for connecting up a lot of the buses are DuPont cables. So these are the sort of ribbon cables with these sort of connectors on the end. And one of the tips I had some time ago from some of the viewers was to actually take these single clips off the end here and replace them with these sort of shells. This is a 12-way one, but normally I'm using the 8-way ones. I just happen to have run out of those. And what I've done is made up a load of cables. So what I tend to do is take this cable, and this one here, for example, I've labelled up is the CRTC D0 to 7 to the video DAC. So this is going to go, in fact, from here to here. So I'll take the label off now that Now generally I tend to use purple is pin 1, which is consistent with the logic analyzers that I use. So generally purple goes to D0, and then you plug this in down here as well. Now we are going to need to plug some other wires in here, but I'll rejig that when we need to. Then I've got another data line here. So this is my CPU D0 to D7. Now this is going to be going to a buffer over here in the final design, but to start with I'm just going to plug this in here So that means we can send that off to the main CPU board. Then we just need to do the address lines. So I've got the address line 0 to 7. So we're just going to plug those in up here. Now there are also going to be address lines down here, so this is probably going to move down here a bit later, but for the moment, and then you can see here on the main address bus is using these sort of power strips, and so they're in twos, so I've actually got the connectors done in twos there. And then finally we've got the upper A8 to A11 address lines, and we're just going to plug those in over here. And we'll need to find somewhere to plug those in. And then finally we also need to wire up the IO read and IO write. So we'll just take those. So that now means that all of the key connections we need, all we've got to do now is to wire this into the main board. We're also going to need to write the software to program the video DAC and the CRTC for the CGA compatible values. Now, these are not going to be able to use the values that are in the default BIOS, because although this is a CGA software compatible card, it produces VGA compatible output, so the timings have to be different. So what I'm going to do in the next video will be plugging this into the main breadboard PC, and then we'll be writing the software to test this, or modifying the MDA video card software to run with this one, and then hopefully we'll be able to get our test pattern. So thanks for watching. If you don't want to miss out on future videos, then please hit subscribe, and if you hit like as well, it just helps to make the videos available to more people. Thanks for watching.